This is going to be a second day of looking at properties of stars, part 2 of properties of stars. So what we know about stars so far, we can determine distances from trigonometric parallax and more. We'll discuss one of those other methods of determining distances to stars later in this video. We can determine the elements present. We look at the spectral lines that we see in the absorption spectrum. Surface temperatures, we know how to do that. A couple of different ways, actually, but mostly from the thermal radiation spectrum. We can determine their luminosities, the total power output of the star. And we can also determine the diameters of the stars. So quite a few different things. There's still more information that we can get from stars. In binary star systems, we can determine the masses of both the stars. And we do this using Kepler's third law as modified by Newton. And we also have to use something called the teeter-totter rule that I'll explain when we get to it here. First, we make a correction to Newton's version of Kepler's third law. Using Newton's laws, the one that we've been using, it looks like this, where p squared is 4 pi squared divided by g, the universal gravitational constant, times the mass of the orbited thing, and that's a constant for any single object that happens to be orbited, and then times a cubed, the semi-major axis cubed. And we've seen this several times this quarter. And if we solve that for mass, we can get that the mass of the orbited thing is 4 pi squared over g times a cubed over p squared. And we did that in the lab, the Jupiter's moons labs. Okay, but the corrected version looks like this. The left side would have the mass of the orbited thing plus the mass of the orbiting thing. Now, we've ignored the mass of the orbiting thing. We could do that when we were studying the moons of Jupiter because all of those moons have very small masses compared to the mass of Jupiter, like maybe millions of times smaller. And so compared to the mass of Jupiter, you could ignore the mass of the orbiting thing. However, you can't always do that. Sometimes we'll have to consider the mass of the smaller thing, especially if we have a binary star system. So we could just call it M1 plus M2 is going to equal that. So that gives us the sum of the masses. And then the more correct version of Kepler's third law looks like this. P squared is 4 pi squared over g times m1 plus m2 times a cubed. Now, Kepler couldn't possibly have known this because his data, even though Tycho's data was very good, it wasn't precise enough to show up the fact that you've got some little dinky thing compared to the mass of the sun orbiting the sun. Jupiter's mass is 1,000th the mass of the sun. So to 99.9% accuracy, you can use Jupiter's mass. Okay. Here's a binary star simulation, and I'm going to have to switch our viewpoint here for a minute once this opens up. Okay, and this has two things of equal mass right now orbiting each other. And so you can see that they both orbit the common center of mass. We can tweak some of the things in here. I can change one of the masses. So now one of the blue mass is 50 times the mass of the red mass. But something that you can see is that they both still orbit the common center of mass, and you have that going on. Now, it would be maybe not too common for a star to have 50 times the mass of its companion, but it could happen. By the way that we learn about these things is by studying the Doppler shifted light that's coming from these two stars orbiting their common center of mass. And so we don't actually necessarily see the two stars orbiting that common center of mass. We could have maybe one of them has a mass of 71 and the other with a mass of 51 or 50, I guess, something like that, some kind of a ratio. And we can do that. You can also change the ellipticity of the orbits to make them more elliptical or less elliptical. We could take it down, give them each a circular orbit. So you can have various things, and you can experiment with things like this. And then when you see light from a star behaving in a particular way, or a pair of stars behaving in a particular way, you can figure out just what their orientation happened to be. Anyway, there's a nice simulation. And I've got the address of it on the slide, so you can go to that if you'd like to see that. Okay. Oops, I have to come back to this side. Once you have that sum of the masses, you can use the teeter-totter rule to figure out the individual masses. And here's the teeter-totter rule. When you have a two-child system, the center point between them, the fulcrum, is actually their center of mass in this case, and it's closer to the child with the heavier mass. The same thing works with stars. Let's see, we'll back up there. But anyway, the mathematics of using the teeter-totter rule is that the lighter mass times the distance from the lighter mass to the center of mass equals the heavier mass times the distance from the heavier mass to the center of mass. And by studying the system carefully, you can figure out the two individual masses. You actually get two equations and you have two unknowns. So it's possible to figure it out. Now, we can also get stars' masses if we can detect planets around them. And more than 5,662 exoplanets have been discovered around more than 4,169 stars as of May 1st of this year. So that's quite a few. And you can get a pretty good statistical analysis of stars by looking at something like this. By the way, exoplanets is a shortened word for what they used to be called, which was extrasolar planets. Extrasolar means around other suns or suns other than our own. So you may hear the term extrasolar planets, including out of me, or you might hear the word exoplanets. Okay, now that we've got another thing about stars added to our knowledge of them, the mass, there's something called the mass-luminosity relation that has shown up. And it's about what you might expect. The more massive the star, the greater its luminosity. And it applies to main sequence stars, and I'll describe that pretty soon here. It doesn't apply to stars that are off the main sequence. It turns out the main sequence stars account for 90% of the stars that we see in the night sky. And the reason for that is that the main sequence lifetime of a star happens to be 90% of its total lifetime. So they spend 90% of their lives on the main sequence. Excuse me. All right, but here's the mass luminosity relation. And by the way, this is a graph that has a logarithmic axis in the vertical and the horizontal direction, which means if you move a particular distance on this vertical axis, you're always moving the same multiple. So you start off at a luminosity of 10 to the minus 4, which is 1/10,000th the luminosity of the sun. And then you make a particular jump and you get up to 10 to the minus 2, which is 100 times as much. And then you go to 1, which is 100 times as much. And then 10 squared, which is 100 times as much. And the same thing happens on the horizontal axis. So if you move from 0.1 to 1, that's a factor of 10 jump. If you go from 1 to 10, you're making the same size jump. And if you made that size jump again, you'd be off the right end of the graph, but that's okay. Anyway, what you see is that low mass stars have low luminosity and high mass stars have high luminosity, just about what you might expect. But it's actually quite a nice linear graph here, not a whole lot of variation. So if you study a star, determine that it's a main sequence star, and you measure its luminosity, you can go from that and figure out its mass if you can't get the mass any other way. So there's something kind of nice about that. Okay, when all of this stuff gets combined, it's put into, humans do a better job analyzing stuff when it's in a graphical form sometimes. And so astronomers started doing this in the early 20th century, and they made these graphs, HR diagram or a Hertzsprung-Russell diagram, after two of the astronomers who were pioneers in making these types of graphs. And something to notice on this, on the vertical axis over here on the left, it has luminosity. And over on the right, it has absolute magnitude. And those can both go on a Hertzsprung-Russell diagram, or either one. You don't have to have both of them. But there is a nice relationship between luminosity and absolute magnitude that can be used. On the horizontal axis, if you look at the one up here on the top, it's got surface temperature, and it does it in kind of a weird way where the highest temperatures are over on the left end, and then you descend in temperature as you move toward the right. So the temperature scale runs in the opposite direction. Down here on the bottom, they have the spectral type of the stars. And this is something I'll address a little bit later. But back in the early 20th century, they were sorting stars into spectral types and then realized that those different spectral types were actually different surface temperatures. So they didn't know that at first. Okay, this is a somewhat different chart, but it's got the main sequence stars along a more of a linear curve on here than they were on the other one. But for main sequence stars, high mass means high luminosity, high surface temperature, and a large radius. Well, low mass means low luminosity, low surface temperature, and a small radius. So characteristics that you might expect. Okay, so making sense out of all that, we can start sorting stars into categories. And originally, this was done based on absorption lines that were present. And here's a graph that shows absorption lines for stars of different types. Type O star up here. Actually, if you go along here, you don't see any hydrogen absorption lines in a type O star. You do see helium-1 showing up here, There's one hydrogen absorption line that shows up on there, or a couple actually, hydrogen gamma and hydrogen beta, but the alpha and the first two helium lines don't show up on there, or some of them don't very well, but they look pretty faint actually. Let's see. The hydrogen gamma, you can just barely see it up here. Okay, type O star. And then you can go to a type B star, and you see various things. All the way out to type M stars, which are the coolest stars. And they had all these lettering for different types of stars. And then they started measuring surface temperatures of the stars and realized that's what they were looking at. So here are the surface temperatures of the stars. The sun would be down here. It's a type G star. I think it's a G2, if I remember right. But anyway, there's stars with basically 6 times the surface temperature of the sun. They're actually hotter stars than that even. But crazy how what a wide range of surface temperatures there are. Okay, and then this is a graph that we looked at earlier yesterday when we were looking at which spectral lines might show up in stars of different surface temperatures. And so it's why for those hottest stars or something above 25,000, you don't see the hydrogen spectral lines so well because they kind of have their peak in stars under about 10,000 Kelvin and start to fade out in hotter ones. And similarly, you wouldn't expect to see any calcium lines, calcium 2 lines, or calcium 1 actually in higher temperature stars because they just don't happen in those. So another way. Okay, and the order from hottest to coolest goes ABA, OBA, FGKM, which the textbook probably mentions the way to memorize this. Goes way back. It's OB, a fine girl, kiss me, or OB, a fine guy, kiss me. That was the way that astronomy students have been doing it for over a century now, I think. And that goes from hottest to coolest. So back to this Hertzsprung-Russell diagram again. And when you make a diagram like this, if you have a truly representative sample of stars, 90% of the stars will fall along this curve in the middle. It's called the main sequence. And then far fewer are shown up in areas like this. By the way, this region down here is where white dwarf stars show up. That'll be the end of our sun's life. It'll end life as a white dwarf. And then up here you've got things like red supergiants and other red subgiants. And in fact, here's one of the ways that they look up here. But you can also, they can plot the sizes of stars on the Hertzsprung-Russell diagram as well. And I'm not sure, 2000. Okay, they've got a logarithmic graph down here for the temperature. So, but anyway, I'm not sure there are stars with 1,000th the radius of the sun or not, but there are. White dwarfs are typically 1/10 or 100th the diameter of the sun, or 100th of the radius of it. And then you can move on up. Stars with 1,000 times the radius of the sun, supergiant stars. There are a few stars where if they were in our solar system, their surface would be beyond the orbit of Jupiter. And so that's just mind-bogglingly large. And then there's another category or categorization thing for stars. And they put a Roman numeral on it. The spectral type is the OBA thing down here that we've got, but it's a luminosity class, 1, 1b, 2, 3, 4, and 5. And the sun is a type 5. Main sequence stars are type 5. But that's another way that astronomers have sorted them into classes. And a way that they can tell whether they're a type 1a, a luminous supergiant, or a less luminous supergiant, or a type 1 or type 3 or whatever, is to study the widths of the spectral lines. This sounds really weird, but here's what's going on. In a main sequence star, the spectral lines that you see in there, the absorption lines, happen in the star's atmosphere, which for a main sequence star is more dense. And the atoms that are absorbing the light that's coming from below, from the surface of the star, or the photosphere of the star, might undergo a collision while they're absorbing that light, or they may just have some Doppler broadening of the absorption lines that happen because they may be moving toward the observer or away from the observer, or toward the sun or away from the sun while they're absorbing the light, or they may undergo a collision at the same time. And that has the effect of broadening the spectral lines, the absorption lines. But in a giant or a supergiant, the atmosphere is way more spread out, way more diffuse. The atoms in it aren't moving as fast because they're usually a lower temperature atmosphere. And so the spectral lines aren't spread out as much. And that's how they can sort stars into these luminosity classes, the type 1 or type 2 or type 3 or type 4. So they can tell the difference by looking at those things. Now, there's a second way to measure distance to stars, and it's called spectroscopic parallax. It's not really parallax because we don't use parallax as the change in viewpoint by looking at something from two different points. This isn't doing that. It's just studying the light from a star and determining what class it belongs to, and we'll back up to here, whether it's a luminous supergiant or a less luminous supergiant. But let's presume for now that it's a main sequence star, a type 5 star. And if it's a type 5 star, main sequence star, it's going to have those broad spectral lines. Okay, so you study the light from the star and you measure its surface temperature. Okay, so you measure the surface temperature, like say you determine that it has a surface temperature of 10,000 Kelvin and it's a main sequence star. Drop down from the 10,000 on this thing to the main sequence, and you can see where it'll be. If it's a main sequence star, you can determine its absolute magnitude by doing that. So if you know it's a main sequence star and you determine its temperature, you can determine its absolute magnitude. Well, you already knew its apparent magnitude probably just by measuring the light coming from it here on Earth, and now you've done something to determine the absolute magnitude. And so, well, here are the steps you go through. You study its light, determine its apparent magnitude, measure its temperature, determine its luminosity class, find it on an HR diagram, and from the diagram, read off the star's absolute magnitude. And then you can figure out its distance from the apparent and the absolute magnitudes. Here's how that'll work. Here's the relation between absolute magnitude, apparent magnitude, and distance. Okay, that's an equation with three variables. If you know any two of the variables, you can determine the third. You rearrange things, you can get little m minus capital M is 5 times the log of d over 32.6 light years. If you've had the quarter of pre-calculus where you play around with logarithmic equations, you'll know how to solve this thing. And you can solve for the distance, which will equal 32.6 light years times 10 raised to the little m minus capital M over 5 power. Okay. You could also have 10.0 parsecs there in front instead of 32.6 light years. But this is another way of getting the distance to stars. And this one isn't limited by distance as like the trigonometric parallax happens to be. That only works out to a few hundred light years. This, as long as you can study the light from that individual star, you'll be able to use this. One disadvantage is, though, that you end up with a range for absolute values, where the main sequence on the Hertzsprung-Russell diagram isn't an infinitely thin line. It's kind of a band of things. And so you don't nail down the capital M all that well. And as a result, this method isn't as precise as trigonometric parallax can be for nearby stars. So it's a little bit fuzzy. It's like you've got a really long tape measure, but it's only got markings every 10 feet. And so you don't get to measure down to the nearest 32nd of an inch or something like that. And then we're looking at the last two slides that we did yesterday again. Here the curve is low for the very luminous stars. The lower left-hand part of this is the stars that have the highest absolute magnitude, also the highest luminosity, and the number of stars per 1,000 cubic parsecs is very low for stars of that type. And for stars that are not as luminous as the sun, stars that are dimmer, and there are much more common. So you can think lower on this graph means less common, higher on this graph means more common. So that works. And then this is that same three-dimensional graph that we looked at yesterday. But now you have a little bit of background into what's going on in here. This horizontal plane down here is the Hertzsprung-Russell diagram. So we've got the absolute magnitude on here. You could also have luminosity on that scale if you wanted to. And then the OBAFGKM there, or this could be a temperature scale as well. But this gives a third dimension to the Hertzsprung-Russell diagram. And that third dimension is showing how many stars of each type might show up. On this one, it's stars per million parsecs. So that's interesting. And the vertical number up here, 10,000 stars per 10 million cubic parsecs, or million cubic parsecs. The red dwarfs there would have about 10,000 of those stars per million cubic parsecs. And that would be a million cubic parsecs. It'd be a cube, 100 by 100 by 100 parsecs. And in that cube, on average, you'd have 10,000 red dwarfs. So that's pretty neat that you can figure that out. So that's a lot more stuff that we can figure out about stars.